So welcome to today class. So in last class we already have discussed the introduction to the fluid mechanics. So today we are going to continue that class. So in last class we have discussed about the different what do you mean by fluid and what are the properties of the fluid. So I think we have discussed about mass density, weight density, and specific weight and specific volume also we have discussed. And if you have not watched that lecture, you go to the description list, there will be the link for that previous class, you can watch that video. So we can continue this yesterday class. So in today class we will discuss the remaining property of the fluid. So the next property of the fluid, that one is called as specific gravity, or that is called as relative density. That is called relative density, or that is called specific gravity. Specific gravity, that is actually denoted by S. So specific gravity of the fluid is can we write down as, that is S will be equal to, so density of fluid, density of any fluid to the density of the standard fluid, density of the standard fluid. And if you multiply G in both numerator and denominator, then also we can write it down as this one is weight density of the fluid to the weight density of the standard fluid. Okay, so this is the formula for the specific gravity. So now the standard fluid, if you consider liquid as water, if you consider liquid, for liquid, the standard fluid is to be taken as, that one is water. And for gas, if you consider the gas, then the standard fluid is taken as air. The density of the water, I told you in last class, that is 1000 kg per meter cube, and density of the air will be equal to 1.21 kg per meter cube. So what is the importance of the specific gravity? So we always compare the specific gravity of a matter, of a substance, with respect to the specific gravity of the water. If you want to find out the specific gravity of the water, that will be density of the water to the density of the now water, and divided by this is density of the water. So that will be equal to 1. Okay. So now specific gravity of the water will be equal to 1. Now you think, suppose I am considering a liquid whose specific gravity will be equal to, suppose I am considering a liquid, suppose oil, I am considering oil. So I am considering oil as a liquid. So specific gravity of the oil will be, that is 0.85, and which is less than the specific gravity of the water, that is 1. So now we can conclude that oil will floats on the water. So now if you write down the phase diagram, you draw the phase diagram, so now oil will be in top side, then water. Okay, because its specific gravity will be 0.85, which is less than what, this is 1. Now suppose specific gravity of the mercury, you want to write it down. So what is the specific gravity of the mercury? Density of the mercury, and this is also coming under the category of the liquid, so the density of the water, standard fluid. So that is 13,600 divided by this is 1000. So that is 13.6. So now it is heavier than water, so the mercury will come here. This is mercury, whose specific gravity will be equal to, 13.6. So by calculating the specific gravity, So we can conclude that the fluid will that matter will float on the water, or it will submerge into the water. If you take the specific gravity of the wood, so it will slightly less than 1, that's why it is floats on the water. Okay, but if you take the specific gravity of the iron, or that is more than 1, so that will submerge and finally it sinks into the water. Now that is the thing. And the specific gravity of any fluid we can calculate by using one instrument, that is called as hydrometer. Okay, that is called hydrometer. So by using this instrument we can calculate the specific gravity of a fluid. Okay, so now we have discussed about four property of the fluid. Now in today class we are going to discuss the most important property of the fluid, that is called as viscosity. So that one is called as viscosity. So viscosity. So viscosity means what? Viscosity means it is the property of the fluid. So it is the property of the fluid which offers resistance to flow. Okay, so viscosity means which offer resistance to flow. If the fluid has more viscosity, then obviously it will have more resistance to flow. So now if you I already told you that according to the Newton's law of viscosity, according to Newton's law of viscosity, yesterday we derived one, that this tau will be directly proportional to, this is d theta by, that is dt. Tau is directly proportional to d theta by dt. What is the d theta by dt? This d theta by dt is called as rate of angular deformation, that is called as, so this tau is directly proportional to, that is d theta by dt, and this d theta by dt is called as, this is rate of angular deformation, or that is called shear strain rate, that is called rate of shear strain. Okay, so and we found out in the place of d theta by dt, we found out in the place of d theta by dt will be equal to, that is du by dy. Okay, we found out this one, du by dy, and this again we write it down as tau is directly proportional to du by dy. Now if you remove this proportionality constant, then this tau we are writing as mu into, that is du by dy. So this is mu into du by dy. So this is called Newton's law of viscosity, and the fluid which obeys this law is called as, that is called as Newtonian fluid, Okay, now let's understand this point. Suppose this is the bed part, and here will be, suppose there will be free stream velocity will be there, this is free stream velocity which does not have any contact with the bed surface, and this bed surface is now stationary. This is stationary in position. Okay, so this is the plate which is now stationary in position. Now this is the free stream velocity, u infinity is called as, this is free stream velocity, mean which does not come in contact with the solid surface. Now and this is has the viscosity, so this one is called as real fluid. Okay, later on I will talk about the classification of the fluid. So there is ideal fluid and real fluid, and this one is real fluid which have some viscosity, which have some resistance, viscosity exists in real fluid. Now what will happen, suppose this fluid particle, when it is come contact with this stationary plate, so at the bottom what will happen, the fluid particle have zero velocity. Okay, the fluid particle have zero velocity. So at, we can write down, and suppose I am choosing one reference axis. So this is my positive x axis, and in this positive y axis. So this is my y axis. So at y equal to 0, we can write down the velocity of the fluid particle will be equal to 0, and this is called as no slip condition. This is called as no slip condition. No slip condition means at this point the fluid particle has the zero velocity, or you can say it will attain the velocity will be equal to the velocity of the stationary plate. Now as you move gradually in this positive y axis direction, so what will happen, now the velocity is gradually will increases. Now the velocity is gradually now increases, and at the final it is attain the again free stream velocity. Okay, attain again after reach at some distance, it will again attain the free stream velocity. So it will have some profile, it will just follow one velocity profile, and this velocity profile is a function of the depth. Okay, it is a function of the y, and suppose I am choosing at y distance, suppose from this point at y distance. So this is my y distance, the velocity of this layer, the velocity of this layer. So the velocity of this layer will be equal to u, and at a distance of from this bed part, that is y plus dy. Y plus dy mean this one is my dy. So the velocity obviously it will greater, that is u plus du. Now this is, suppose I am choosing this one as 1 and this one is 2. Now actually I will separately study this part. Now I will separately study this part. Okay, let me study that one. Suppose this is my bottom layer which is moving with a velocity of u, and suppose this is my top layer, and which is now moving with a velocity of, that is u plus du, and in between the gap is this one is dy. Now what will happen, you just imagine, now this top layer, this is one, and this second layer. So this second layer is now try to accelerate this bottom layer. Okay, it will try to accelerate this bottom layer, but now as the bottom fluid layer is now, it is not moving as compared to this second layer. So what will happen, it is moving with a less velocity with compared to second layer. So it will now try to retard the second layer motion. So there will be relative velocity will exist in between these two layers. Because of that, what will happen, this will offer a resistance to the flow, because the first layer will try to retard the motion of the second layer, and the second layer will try to accelerate the motion of the first layer. That's why what will happen, there will be shear stress will be, or shear force will be generated in between that, because of the relative motion in between this fluid layer, because fluid always moves in layer manner. So as there will be some relative velocity will come, so that will leads to the shear stress in between this layer. So now if you imagine the, suppose this is my, you can imagine, so this is the surface area A. So this surface area A, so the what is the shear stress will exist, the shear force divided by this tangential area. And also we know the shear stress already we written, this is mu into, this is du by dy equal to shear force by area. Now what is the shear force if you want to calculate, that is mu into A into this is du by dy. Now what is this velocity gradient we have to take. Okay, what is the velocity gradient we have to take? Let's talk about now in detail. So now I told you this tau will be equal to mu into du by dy. Okay, this is called Newton's law of viscosity. That is called Newton's law of viscosity. And the fluid which obeys this Newton's law of viscosity, that is called as Newtonian fluid. Okay, that is called as Newtonian fluid. Now what are the classification, which fluid will come under the category of the Newtonian fluid? So the best example is water, okay, oil, kerosene, benzene. So these are the fluid which is come under the category of the Newtonian fluid. So this Newton's law of viscosity, the fluid which does not follow this Newton's law of viscosity, that is called as non-Newtonian fluid. That is called as non-Newtonian fluid. That we are going to discuss after few slides. Now yesterday we have discussed about the, just wait for that one, the du by here I told you du by dy, I will tell you how you to find out. So yesterday actually we discussed about the unit of the dynamic viscosity. Okay, so dynamic viscosity unit we written SI unit as I already derived, that is called Newton into second by this is meter square, and the MKS unit also we have found out in last class, you just watch that one, that is kg by this is meter into second. And if you want to write down this CGS unit, that is called as dyne Newton, we can write into second divided by this is centimeter square. Obviously this will be equal to the MKS unit. If you write down this CGA, that is gram per centimeter into this is second. So 1 gram we can also write it down as this is 10 to the power minus 3 kg divided by this is 10 to the power minus 2 meter into second. So now this kg meter second is also now equal to the Newton meter square per second. So we can write it down, and this dyne second per centimeter square, this dyne second per centimeter square is called as poage. This one is called as poage. So we can write down this is 1 poage will be equal to 1 by 10th, this is Newton second by meter square. Or we can write it down this 1 poage will be equal to 0.1 Pascal second. This is very important, because if it is given in poage, definitely you have to convert into the SI unit, then you have to solve. So always remember 1 poage will be equal to 0.1 Pascal second. Okay, now let's discuss about that one. Now we discuss, so already discuss about this tau is directly proportional to this d theta by dt, and this is we can write down this is tau will be equal to mu into this is du by dy, because d theta by dt will be equal to this is du by this is dy. So this is Newton's law of viscosity. Now you just see this equation, this is similar to a straight line equation. If we write then this is y equal to mx plus c, here c will be equal to 0 and x will be equal to this velocity gradient, and this one is a slope. Okay, so now if you draw, this one is a graph. So this is, if you take y will be in stress in y axis and the velocity gradient du by dy, or we can say this is d theta by dt in x axis. So this is just a straight line, and the y intercept will be equal to 0. So this is just a straight line, and the liquid which follow this straight line, that is coming under the Newtonian fluid. That is coming under the Newtonian fluid, and the slope will be equal to the dynamic viscosity of the liquid. So now, for example, there will be two fluid will be there. Suppose this is the shear stress in y axis, and this is velocity gradient du by dy in x axis. Now suppose there is two liquid will be there, A and B. Now you tell me which liquid A has more viscosity. Suppose this angle will be theta A and this angle will be theta B. So I told you this slope of the curve A, that is nothing but the, if here theta A is greater than the theta B, so this slope is nothing but it will be equal to the dynamic viscosity of the liquid. So obviously dynamic viscosity of the curve A is greater than the dynamic viscosity of the curve B. So that slope of the Newtonian fluid curve, the straight line curve, is equal to the viscosity of the liquid. So that is the thing. Now variation of shear stress. Suppose this is my stationary plate. And the velocity profile here I am choosing to be a non-linear profile. The velocity profile I am choosing as this one is a non-linear profile. So this is my non-linear profile. This is non-linear profile. Okay. So now this is my positive x axis and this is my positive y axis. Okay, and here this is u is a function of the y. Again I am choosing another profile, velocity profile. This is my stationary plate and the velocity is, this is my y and this is my positive x axis. Here is the velocity profile I am choosing as this one as a linear one. So this one is one linear one. Okay, this is also a linear profile, linear velocity profile, this is also velocity is function of y. Now we have to compare. Okay, so because the basic equation will be equal to tau will be equal to mu into this is du by this is dy. This is the basic equation. Now suppose I am choosing two layers. This is my first layer and this is my second layer. Now you have to compare the shear stress, variation of the shear stress in between these two layers, whether the shear stress will remain constant throughout this profile, whether the shear stress will be vary in all the profile. We have to understand first this one, non-linear profile. Now if you draw a tangent, okay, now if you draw the tangent so this, if you draw a tangent, so suppose I am drawing a tangent at this point, and suppose this second layer, the second layer will be at a distance of this is y plus this is dy, that is moving with a velocity y plus du, and this first layer is moving with a velocity of u, and suppose this is a distance of y from the stationary plate. Now if you want to find out this slope, then what will happen? So this obviously this will be equal to, so this slope will be equal to this by this. Suppose this slope will be, I am taking this is alpha, and this slope will be equal to, so this slope if you write down, if you compare, this slope will be equal to, so this one will be equal to this by this, or if you want this one, this beta will be equal to, because this is alpha, or let me clear this figure, again. So this is the velocity profile. Okay, here I am drawing a tangent. Okay, this tangent at this point, this one is called as alpha, and if you want to measure this vertical distance, this one is called as beta. Okay, this one is called as beta. So this alpha will be equal to, so this one is, okay, so this is dy and this distance will be equal to, this is du. So this tan alpha we can write it down, this is dy by this is du, but we want du by dy, so this du by dy will be equal to 1 by this is tan alpha. Now you see, as you are moving as you are moving in forward direction, so as you are moving the forward direction, the alpha value is now increasing. Okay, so as you are moving in forward direction, the alpha value is now increasing. If the alpha value increases, then the du by dy also tan alpha increases, and tan alpha increases means the du by dy is decreases. Means we can say the shear stress profile at this profile, this is one profile and the second profile. So shear stress as first profile will be greater than the shear stress at second profile, because the alpha is now increasing in forward direction. So what is happening, the shear stress also decreasing. Okay, so that is the thing. So now if you ask me at which point the shear stress to be a maximum, so here what will happen, here what will happen, the alpha to be minimum, because this is now parallel to this one. So if you draw the tangent, the slope is almost will be equal to less, very less, very that can be less. So if alpha will be very minimum, then what will happen, that du by dy will become maximum. If this will become maximum, obviously the shear stress will become maximum, and that shear stress is called as wall shear stress. Okay, that wall shear stress will be equal to mu into this is du by dy. So what actually I am trying to say you, if the profile, if the velocity profile will be mentioned in the problem, then you have to find out the du by dy at that particular point, and at that particular point you have to find out the shear stress at that layer, because the slope is now keep on changing if you change the y. Okay, so at particular layer the shear stress will not remain constant. Okay, so shear stress at point number 1 will not be equal to shear stress point number 2, or it is not at wall shear stress. So for that we have to find out the velocity profile du by dy, and the slope we need to find out. After finding out the slope, we have to find out the shear stress. Now in linear profile what will happen, now you see at all points, suppose this is my 1 and this is 2 point, all point the slope will be remain constant. So all the point this alpha will remain constant, so the what will happen, this du by dy also remain constant. So as the du by dy will be remain constant, so this shear stress also will be equal to same in all the case. Tau 1 will be equal to tau 2 will be equal to, there will be tau wall shear stress. This is the tau wall shear stress. So what will happen, here the shear stress will remain constant if the profile will be linear, but if the profile is non-linear, then the shear stress will not remain constant. So we need to find out the shear stress if we need to find out at each layer. Before that we need to find out the slope of that at that particular point. Okay, the du by dy you need to find out, then after finding out the slope, then we need to estimate the shear stress if the velocity profile will be non-linear. If the linear profile, wherever you find out at this point, at this point, or this point, or that point, the shear stress will be always remain constant, or it will remain same, it will not change. So that's why for this non-linear point of view, the shear stress is always written y, this is mu into this is du by dy at particular y, at particular y. So this is the shear stress for non-linear profile, velocity profile. But here the shear stress is always tau 1 will be equal to tau 2 will be equal to tau 1 will be equal to mu into this du by dy. Okay, so for this, if in problem the velocity profile is mentioned, then go by this way. If it is not mentioned, then you have to assume the profile to be a linear profile and then you proceed the numerical. Okay, because you can imagine that gap in between these two layers will be 0.0325 millimeter. So there the velocity profile is assumed to be taken as linear. Most of the time in GATE exam or in semester exam, the profile to be given as a linear profile. Okay, linear profile. So directly you have to use the formula and you have to estimate the shear stress. Now we have to find out now viscosity effect of temperature and pressure on viscosity. Effect of temperature and pressure on viscosity. Now first of all, you should understand viscosity is due to two things. Okay, viscosity in a fluid. Viscosity in a fluid exists due to two things. So first one is called the cohesive force. The cohesive force among the fluid particle, and second one is called molecular momentum exchange. In short form, that is MME, and this is CF. So viscosity in fluid exists due to the two things, that is first one is cohesive force and second one is called molecular momentum exchange, and this one actually exists in liquid, this cohesive force, and this one in gases. In gases the cohesive force will be very less because the gaseous molecule will not be present with each other, they will move randomly apart from each other, so that's why the cohesive force in gas molecule is negligible. But what will happen in case of gases, they will collide with each other, they will transfer the momentum with each other so fast that the viscosity will increases. Okay, so now what is the effect of temperature? Let me talk about first. So effect of temperature in liquid. First over in liquid, fluid, liquid and gases. Separately I will discuss about liquid. So what will happen if you increase the temperature? So if you increase the temperature in liquid, then what will happen? The cohesive force means the intermolecular force of attraction in between this molecule. The intermolecular force of attraction in between the molecules will decreases because the bond in between these molecules, so there will be intermolecular force of attraction. So what will happen? That bond will breaks. So as a result, what will happen? The intermolecular force of attraction will break down. So as a result, the viscosity also of that fluid will be break down. Means the cohesive force will be more strong, then the viscosity of the fluid will be more strong. If by means of any way, if you break down the cohesive force in between these molecules, then the viscosity will be decreases. And the similarly, if the temperature decreases, then cohesive force increases and the viscosity also increases. So you can imagine of ice. Okay, now in case of gases, so in gases what will happen? If the temperature will increases, then the molecular momentum exchange, that is also increases, means they will move very fast, very quickly. Okay, and they will excite with each other and they will collide with each other and they will transport the momentum with each other. So as a result, what will happen? They will, the frictional resistance among the molecule increases. So as a result, molecular momentum increases. So as a result, the collision in between these molecule increases. So as a result, what will happen? The frictional resistance in between this molecule, because they will now slide or collide with each other, so the resistance will increases. So as a result, the viscosity increases. So similarly, if the temperature decreases, molecular momentum exchange in the gases decreases, the viscosity also decreases. So if you ask me the equation for this, the viscosity actually related to a liquid, that is mu 0 divided by this is 1 plus alpha t plus beta t square. So mu 0 is the viscosity at 0 degree Celsius, and alpha and beta are called constant. Alpha beta are called as constant. So here also we can relate this mu is inversely proportional to temperature. If temperature increases, in the case of liquid, the viscosity decreases. So here also one equation will be there, mu will be equal to mu 0 into 1 plus alpha into t minus beta into t square. Here also viscosity at 0 degree Celsius of the gases and alpha beta are constant. Here you can see mu is directly proportional to temperature. If temperature increases, then viscosity increases. So we need to understand this thing in a graph. So for that we need to draw a graph. This is the temperature in x-axis and viscosity in y-axis. So for liquid, the increase in temperature, the viscosity decreases. So this is the equation of the liquid, and for gases, if you increase the temperature, the viscosity increases. This is the gases. Okay, so I hope in today's lecture we have gone through. So the remaining property, relative density, specific gravity, this is density of the fluid to the density of the standard fluid, and for liquid the standard fluid taken as water, and for gases standard fluid taken as air. So density of the water, this is 1 gram per cc or 1000 kg per meter cube, or density of the air will be 1.21 kg per meter cube. And specific gravity importance is that if we can compare the relative weight of the two matter. If you compare the oil and water, obviously the specific gravity of the oil is less than water, so it will float upon the water. Then we discuss the most important property. From this chapter you will get most of the numerical, that is called viscosity. It is the property of the fluid which offer resistance to the flow, or which offer resistance against flow. So we know that Newton's law of viscosity from the previous classes. This is tau is directly proportional to d theta by dt, and this d theta by dt is called a rate of angular deformation, or that is called shear strain or rate of shear strain. And this already derived, this d theta by dt will be equal to, this is du by dy. So we can write down this is Newtonian fluid, and this is called Newton's law of viscosity. This is called Newton's law of viscosity. And after that we have compared, this is in between the how we can find out the shear stress. Okay, this is the mu into du by dy. So then we discuss about the unit. 1 Po is equal to 0.1 Pascal second. Then we compare the viscosity of the two fluid. Then in linear profile also we can find out. So now here so thank you for today class. In next class I will come with